Hi, thank you very much. First of all, I would like to thank the organizing committee, in particular Dion, for inviting me here today. As Dion says, I'm an outsider. I'm probably the only one that will present with having a slide about conflict of interest. I didn't know that that's the etiquette, but I think reliably I'm probably the only one that really doesn't have any conflict of interest here. So, check that. Yeah, sorry, got it. So, like Dion said, we had a discussion around 4 months ago, and we kind of thought of whether we can apply some of the work that we are doing. Like Dion said, my background is in genetics and in bioinformatics, and we wanted to check whether we can adopt some of the techniques that we have been developing for quite a few years now and see whether we can apply them for the questions that Dion just pointed out. What Dion also asked me was to give you a very brief, he said, one-slide introduction to what is bioinformatics. I've been working in this field for quite a few years, never been asked to present it in one slide, so I wasn't really sure what to say. So I Googled it, and I found some definitions. One that I particularly liked was from the online Oxford Dictionary, where it defined bioinformatics as a new science that deals with collecting and analyzing complex biomedical data set. And I like this definition because it contains two crucial parts. One of them is about developing novel methodologies for collecting, that includes integration, comparison of data, and then analyze them to form hypotheses. And this data set needs to be complex, otherwise, first of all, I wouldn't be really interested into them. And then we also have techniques for many, many years that could be applied. So we have to have some complexity in order for bioinformatics to shine, if you like. And then I turned into the source of truth, as we all know it, Wikipedia, where I found a huge description about what bioinformatics is. And I highlighted some areas, primarily because I wanted to point it out that what bioinformatics does, it's basically borrowing principles from different domains, computer science, artificial intelligence, information technology, in my case, philosophy. I don't have time to talk about this today, but I'm really interested in philosophy. And we apply them and combine them together in order to identify ways that we can extract meaningful associations from large data sets and hopefully provide some explanation from our results. What probably is interesting within the context of our discussion today is some work that I've been doing over the last 15 years to enable the comparison of phenotype information in a similar efficient manner that we do for genomic, proteomic, and so on information. And for that to be achievable, we need to somehow be able to integrate information across different domains of knowledge, level from granularities, ranging, if you like, from the molecular level all the way up to the phenotype, the whole organism level. And I'm giving an example of my own research. It's in cardiovascular. I'm interested in rare diseases. And you see here we are integrating from the molecular, the omics studies, these data sets, all the way up to unstructured images, MRIs in this case, ECGs, electronic health records, clinical knowledge, and so on. We bring them everything together in order to understand better the pathophysiology and pathobiology of disease, and in this case, identify variations. Now, when I described this to Dion, he said, well, hang on, do you think that we can apply this to our own problems? And he started talking about this data set that were introduced to you, these two independent studies that he sent the data to me. And he asked me whether we can apply a similar kind of techniques, create similar kind of phenotype profiles to see whether we can predict anastomotic leak. Now, before I move on to the results, which, as Dion said, are very, very preliminary, what I would like to point out is some considerations we need to take into account. And I'm only using some abstract information. There are quite a few, but I just wanted to make some pointers. One of them is that people like myself, we really need to understand how these data were collected. I know Tom and Dion and the consortium are putting now rigorous SOPs about how this data is collected. We also need to understand what's the relation of these parameters, why it's important, why you as surgeons think that these parameters are the ones that you should be collecting about your patients, and what do you think that this means. Then we need to understand how complete these data are, what's the value. I'm going to give you some examples later on. And finally, as far as I'm concerned, I need to understand the molecular pathophysiology and pathobiology that gives rise to these phenotypes that hopefully have some influence over the surgery outcomes that you are performing. Now, in relation to these two examples that I mentioned, data completeness, I am pointing out here that we took one of the studies, the stoma study that was given to us. We took up the patients that have some positive outcomes, so they have some leakage. And you see here on the bottom line the parameters that have been collected for these patients. Now, unfortunately, for this particular subset, there is a very small subset, thankfully not many of them leaked, we were missing quite a few data that you can see here. And actually some of the ones that we already have, such as indication or urgency, it didn't really matter because they are, for example, in stoma, it's always elective, so we couldn't use that parameter. So building this phenotypic profile had some limitations, primarily where we were missing this kind of data. And we're investigating ways of retrieving them or figure out what we were doing wrong, maybe there was something wrong with the data, how it was passed on to us. Then another important issue about data and their value, this is undoubtedly a unique and invaluable data set. But we need to understand how reliable the data is, how can we interpret the relations amongst these data sets. What I'm presenting you here is again from the same study, these different participating countries, the leakage rates as it has been reported in the data set that we were given. And as you can see in the top left-hand side, we have countries that have almost 0% of leakage rates. There's one of them that has more than 200 patients, and only 6 of them leaked. Definitely a country that I would like to have an operation if I was having this type of operation. Whilst on the other side, you see countries going up to 80%. So there's a big difference in this scenario as to how these things are reported. It might be true. It might be that there is something about the training that, or it might be how the biology of each patient gives rise to different outcomes. But I strongly suspect there must be something about how the data is collected, how it's been reported, how consistent they are. So we need to identify how and understand this data, because it's obviously very valuable, and we need to ensure that we are exploiting its true value. Now, in respect of that, we started having some agnostic stabs in this data set using the techniques that I mentioned earlier on. The first thing we did was we took this stoma study and we selected 5 of the countries that were sitting there in the middle in the table that I saw earlier on. So basically, they had enough patients and they have an average leak rate. And then we use the parameters you see here that have data for these patients, and we applied a variety of different models stemming from artificial intelligence. I'm giving some examples from machine learning. And we tried to create stratifiers, classifiers, to see whether we can predict the outcome. And these are the results. I mean, I think you're very familiar with this idea of ROC analysis. Basically, it's the sensitivity of a classifier to rank higher a set of random chosen positive examples from a set of random chosen negative ones. And as you can see, the value we have here is around 0.69. So it's not really an impressive number. However, I think it does give us an indication that there is a signal. It looks like this generation of these phenotypic profiles allows us to somehow distinguish between these 2 patients. And that's evident in this sensitivity and the score that you see there. Although our specificity is fairly low, so we're predicting a lot of false positives, our sensitivity is quite high, almost 0.9, which means that the patients that we're predicting to be leaking were almost always correct. And that reflects what Dion refers to as the leak risk, we refer to as negative predictive value, which goes up to 24%. Which, as I understand from Dion, the current state of the art is around 8 to 10%. So I think we are beginning to have a strong signal. So, one thing that was important for me, though, from this study is this flattening dip here you can see in the ROC curve. Basically, it looks like that some of the patients that have a positive outcome, the phenotypic profile seems to be mimicking a lot the patients that have a negative one. So in other words, we cannot distinguish, for some cases, we cannot distinguish between the 2 patients whether they're going to leak or not. And this is something that we started investigating. We tried to see what kind of factors, how can we distinguish, how we can stratify these patients. And one of the important factors that, from our analysis, seems to be the type of operation that it was performed on them, whether it was a laparoscopy or an open surgery. So I turned to Dion and I formed that hypothesis to him, and he tried to explain it to me. And it turns out that, I think, contradicting what we heard earlier on, maybe surgeons, maybe you are very, very good at picking patients that are high and low risk. And according to Dion, the high risk patients always, you seem to guide them to open surgery, where the low risk to laparoscopy. So maybe you have this ability, this innate ability to pick the different risk groups. So we want to exploit to test whether we can use that. So what we did is we took laparoscopy patients that didn't leak, and we combined them with open surgery patients that had positive and negative outcomes. And we formed the same hypothesis. Can we predict who is going to leak and who is not going to leak? We use these type of parameters that were available and a similar type of approach. And these are the results now. You can see now we have a fairly big increase in this ROC curve. We're almost to 0.8. So we're moving from this signal that we thought we have to actually a strong indication. And that's is reflected in the sensitivity. It's over 0.9. So we're almost always correct for picking the right patient that's going to leak. Our specificity is, again, a bit low, so we have, again, a lot of false positives, but it does mean that for a few or a subgroup of patients, we are very, very accurate for predicting that they're going to leak. And that's reflected in this negative predictive value, this leak rate, which is now around 30%. So we are increasing dramatically. But I think the main point that I want to draw for this is not these results I could present. We have run a lot of different models. We have a lot of different results associated with them. I think the main thing that I want to pass on today as a message is that as you're collecting more data, as we understand how this data is being collected, what's its value, what's its relation, what's your hypothesis, as we are becoming more aware of your underlying knowledge, I think we have a chance, or a feasible chance, of actually being able to stratify these patients, stratify the factors, divide them, if you like, between patient-specific profiles, disease profiles, surgeon profiles. Even I, as a surgeon, understand that somebody that is older and has a higher as a grade, the probability is that he has a lower, higher probability of leaking. But that's not very useful since you cannot affect that. But if we can understand the relationships between the different factors, we can perhaps create subpopulations that can dictate what type of operation we're going to have, whether they should indeed have any operation at all. So I would like to leave it at that, and thank you very much for your time and attention.